Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, Chemical Bonding. Today we will begin with lecture 25 from the course, but make sure you watch the previous ones before viewing this one. So in the last lecture, we discussed what is hybridization, what are the salient features of hybridization, what are the important conditions necessary for hybridization. And I'll try to sum up everything so that it will be a quick revision of the last lecture. Well, hybridization is the phenomenon when there is intermixing of atomic orbitals. But what atomic orbitals? The orbitals of the valence shell and sometimes the d orbitals of the penultimate shell. And these are the ones which are going to consist of unpaired electrons or paired electrons, but never those orbitals which are empty. And this means that the orbitals which are participating in hybridization, these are the ones which are going to form sigma bonds, or these are the orbitals which are consisting of lone pair of electrons. So these will never be the orbitals which are going to participate in pi bond formation. Once the intermixing of these orbitals has taken place, the orbitals, they will redistribute their energies to form same number of new orbitals which are identical to each other, and these orbitals are going to be called as hybrid orbitals, and the phenomenon hybridization. Right? So I hope the whole concept is clear to you people. And now we will be carrying on the discussion further, and we will be seeing what are the different types of hybridization. And one of them, the first one we will be discussing today in this lecture in detail, is going to be sp3 hybridization. So the types of hybridization basically is based on the types of orbitals involved in mixing. And on this basis, the types we have are sp3, sp2, sp, sp3d, sp3d2 and sp3d3. Okay, and we will be discussing them one by one in detail. The first one, as I told you, we are going to discuss in today's lecture is sp3 hybridization. And as the name suggests, this is formed by the mixing of 1s and 3 p orbitals belonging to the valence shell of the atom. And how many orbitals are going to be produced? Well, it is going to be 1s and 3p. So total 4 orbitals are mixing. So we will get 4 new hybrid orbitals. What will be the name of these orbitals? All of them, they will be called as sp3 hybrid orbitals, and all of them, they are going to be identical to each other. And now once these hybrid orbitals have been formed, they will be directed towards the 4 corners of a regular tetrahedron, and they will be making an angle of 109 degree 28 minutes with one another. And now let us understand what all this means. Well, first of all, you should know what is an orbital. An orbital, this is a three-dimensional region in space where the probability of finding the electron is maximum. So we can say that an orbital is an area of high electron density. So if after sp3 hybridization, we have got 4 hybrid orbitals, we can say that we have 4 regions of high electron density. And doesn't this sound somewhat similar to the 4 electron pairs we were discussing in the VSEPR theory? The only difference in this case is in the VSEPR theory, we talk about electron pairs around the central atom after the bonding has taken place, while in hybridization we are talking about hybrid orbitals or regions of high electron density before bonding has actually taken place, right? So 4 electron pairs, according to the VSEPR theory, they were directed towards the 4 corners of a regular tetrahedron. So they were at a minimum repulsion from between the electron pairs. And similarly, now we have 4 hybrid orbitals, and these 4 hybrid orbitals are the areas of electron density. So this means that they are going to consist of electrons. They may be paired electrons, they may be unpaired electrons, but they are electrons in the 4 hybrid orbitals. And so that there is minimum repulsion between these 4 hybrid orbitals electrons, these hybrid orbitals, they will be directed along the 4 corners of a regular tetrahedron. And I hope now you can draw a resemblance to both of these things, the VSEPR theory and the hybridization. Both of us are giving us an indication of the geometry of the molecules, right? In VSEPR theory, it was the electron pairs. In the hybridization, it is the direction of the hybrid orbitals, which is giving us an indication to the geometry. So when we have 4 hybrid orbitals, the hybridization is sp3. The geometry of the molecule is a tetrahedral geometry, and therefore we call it also a tetrahedral hybridization. Now these sp3 hybrid orbitals, they are going to have a 25% s character and 75% p character. Why? It is simple to understand. 1 out of the 4 orbitals which were combining was an s. So 1 out of 4 is 25%, and similarly 3 out of 4 is 75%. So sp3 hybrid orbital, this consists of 25% s character and 75% p character. Some examples of sp3 hybridization, they are of the molecules ethane, C2H6, methane, CH4, water, H2O, ammonia, NH3, sulfate ion, SO4, 2 negative, etc. And we will discuss a few of them so that the concept becomes clear to you people. So here we have the different types of orbitals. You will be able to see diagrammatically we have 1s, 1px, 1py and 1pz. So these are the 4 orbitals which are going to combine with each other, and as a result what we will be getting 4 hybrid orbitals. And you can see now all the 4 of them, they are identical to each other, all having a big lobe and a small lobe, just similar to each other, same shape, same energy, but they will be directed towards different directions. That is the only difference over here, right? So we have got now 4 hybrid orbitals, and they are going to be directed towards the 4 corners of a regular tetrahedron, right? And now while we are representing these 4 hybrid orbitals together, what you are seeing is only the big lobe. Okay, so you can understand this, that probably the small lobes, they have been hidden by these big lobes, so they are not visible. Okay, so we have just a representation where you are able to see the big lobes and not the small lobes. Some places you may see that in the figure there is a representation of the smaller lobe as well, but generally you will be finding that only the big lobe is represented. So you have to understand that this is one hybrid orbital, this is the second, the third and the fourth hybrid orbitals which have been produced by the hybridization of 1s and 3p hybrid orbitals. So let us see the first example where we are going to see the sp3 hybridization, the formation of the methane molecule CH4. So CH4, there is 1 carbon atom and 4 hydrogen atoms. And one thing remember over here, that this is carbon which is going to hybridize. Hydrogen can never hybridize. Why it can never hybridize? Because this consists of only 1 electron. So 1 electron means there is 1 half-filled orbital. If there is only 1 half-filled orbital, whom is it going to mix with? At least we need 2 half-filled orbitals which can mix with each other and undergo hybridization. So hydrogen can never undergo hybridization. Okay. The next thing now we have is that we have carbon, and carbon is forming 4 bonds with hydrogen, as you can see in the formula. right? So if it has to form 4 bonds, it needs 4 half-filled orbitals. If we see the ground state configuration, there will be only 2 half-filled orbitals, but in the excited state, we see the electronic configuration of 1s2, 2s1, 2px1, 2py1, 2pz1, which means that there are 4 half-filled orbitals. So these 2s, 2px, 2py, 2pz, these are the 4 orbitals now which are going to intermix with each other, and as a result of this intermixing we will get 4 new hybrid orbitals. And these hybrid orbitals, what is going to be the name of all of them? They are going to be sp3 hybrid orbitals, right? So by the mixing of these, we get 4 sp3 hybrid orbitals which are going to be directed in space as a corners of a regular tetrahedral. So we see a tetrahedral geometry for these sp3 hybrid orbitals over here. Now, next let us see the energy considerations that are going to occur over here. So the 2s orbital, which was at a lower energy level than the 2p orbitals, right? So the energy difference between them is not much because they belong to the same principal, quantum number 2, but there is an energy difference. And one of the 2s electron, this moves into the 2p orbital, so there they are 4 half-filled orbitals, and then after this they are going to hybridize with each other, and as a result we get 4 hybrid orbitals, the sp3 hybrid orbitals, all of them consisting of 1 electron, and all of these they are similar to each other, all of them they are equivalent in energy. And if we sum total the energy of these 4 hybrid orbitals, this will be always less than the sum total of these energies of the 4 pure orbitals which prior to the hybridization. Okay, so the energy level is less, the energy of these orbitals is less, that is why they form more stable bonds. So we have now 4 sp3 hybrid orbitals of carbon. So now what we see is this position where we have carbon with 4 hybrid orbitals, and surrounding this carbon there are 4 hydrogen atoms, and these 4 hydrogen atoms they have 1 s orbitals in which there is 1 electron, right? So 1 s orbital of each of the 4 hydrogen atom overlaps with one of the 4 sp3 orbitals of carbon to form a sigma bond, right? And now these all orbitals they are similar in to each other, and these are the ones which are forming sigma bond. A sigma bond will be always formed by a head-on overlap, never is going to be there a sideways overlap. Okay, one thing, this is very important that you have to remember. Now the overlapping, what is going to result in? This is the formation of the methane molecule, where you can now see that there has been a overlapping between the sp3 hybrid orbital and the s orbital of hydrogen. So what have we got as a result? We have got the formation of 4 strong equivalent carbon hydrogen covalent bonds to produce the methane molecule. And now what is the geometry of the methane molecule? It is the geometry of the 4 hybrid orbitals, right? So the orbitals they have given the direction to the molecule, and we as a result get a tetrahedral geometry for the methane molecule. And because all of these orbitals now they consist of bonded pair of electrons, so the shape is also going to be in accordance with the geometry. The shape is also a tetrahedral shape. Next, we consider the formation of the ethane molecule, which has the molecular formula C2H6. So C2 means that there are 2 carbon atoms, and H6 means there are going to be 6 hydrogen atoms. As a result, what we are going to see is again the 2 carbon atoms they are undergoing sp3 hybridization. We will get 4 hybrid orbitals for each carbon atom, and again the other also you can see that this is sp3 hybridized, and they are surrounded by 6 hydrogen atoms. So what do we see over here? We are going to see that an sp3 orbital of one carbon is overlapping head to head, or you can say end to end, with an sp3 orbital of the second carbon to form a sigma bond between the two carbons. So you can see this, there is a sigma bond formation between the two carbon atoms. And what about the three remaining hybrid orbitals? Yes, they are going to overlap with the s orbital of the hydrogen atom to form a carbon hydrogen sigma bond. So this is a carbon carbon sigma bond, this is a carbon hydrogen sigma bond, and as a total we have got 7 sigma bonds formed over here, right? And both the carbons, they are sp3 hybridized carbon. So all the bonds, they are going to be equivalent over here, okay, because the hybrid orbitals, they are identical to each other. One more thing that you have to remember is that the orientation of the two CH3 groups, this is not fixed relative to each other, right? So we know that a sigma bond, around the sigma bond, free rotation is possible. So this CH3 carbon and 3 hydrogen, so this forms one CH3 groups, this forms the other CH3 group, and if you consider this to be the sigma bond 1, so here the CH3 group, this can freely rotate, this can freely rotate about its own axis, and therefore the position of these two is not going to be fixed relative to each other. They can move independently of each other, okay. Now, while discussing hybridization in the last lecture, I told you that a hybrid orbital can consist either of one electron or two electrons, but never it is going to be an empty orbital, right? So let us consider an sp3 hybrid orbital, which is going to now have a lone pair of electrons. The example we are taking here is first of the ammonia molecule, and here ammonia has nitrogen as the central atom. So first of all, write down the electronic configuration of nitrogen: 1s2, 2s2, 2px1, 2py1, 2pz1. So this means in the ground state, nitrogen is having how many half-filled orbitals? It is having 3 half-filled orbitals. How many bonds has nitrogen to make in ammonia? It has to make 3 bonds. So 3 bonds, it has 3 half-filled orbitals, so it can form overlapping with the hydrogen atoms to form the 3 sigma bonds. Now, because we need orbitals which are going to be identical in nature, so nitrogen has to go a hybridization. And what type of hybridization? It consists of 3 p orbitals where there are 1 electron each, and 1 s orbital where there are 2 electrons. So this means that there are 4 orbitals which have electrons in the valence shell. These 4 orbitals are going to undergo hybridization, and as a result of hybridization, when there are 4 orbitals which are combining, it is going to be a sp3 hybridization, right? And when we have a sp3 hybridization, what is the geometry of the molecule? The geometry of the molecule is going to be a tetrahedral geometry, right? Now, when we have a tetrahedral geometry, after that, when the hybridization has occurred, because one of the orbital consists of a lone pair, the orbitals which are going to consist of unpaired electrons, they will come closer to each other so as to minimize repulsion. And because of that, the angle between the orbitals, that is going to decrease from what we saw in the CH4 molecule, right? So there the angle was 109 degree 28 minutes. Here we have 107 degree and 107.8 degrees. Now, once these orbitals, they have arranged themselves in the 3-dimensional space, the orbitals, the sp3 hybrid orbitals, which consist of 1 electron, they are going to overlap with the 1s orbital of hydrogen, and there is going to be the formation of a sigma bond, right? So the geometry what we discussed is a tetrahedral geometry, because there are 4 orbitals, they are going to direct each other in space as a tetrahedral geometry. But when we consider the shape of the molecule depends upon the position of the atoms, right? So according to the position of the atoms, this is the position of the atom. So we get this as a distorted tetrahedral shape, or you can say that this is going to be a trigonal pyramidal shape, right? So you can see this is a pyramid being formed on a base, you can say. So we have a trigonal pyramidal geometry for the ammonia molecule. Next, we have an example of the water molecule. Again, for the water molecule, oxygen is going to be the central atom. So write down the electronic configuration for oxygen. So oxygen is going to have electronic configuration of 1s2, 2s2, 2px2, 2py1 and 2pz1. Right? So oxygen has how many orbitals which are half filled in the ground state? It is 2 orbitals, right? So 2 orbitals, and in the water molecule, oxygen has to form how many bonds? It has to form 2 bonds with the hydrogen atoms to give us water molecule, right? So 2 orbitals are consisting of 1 electron each, 2 orbitals are consisting of 2 electrons. A total again we have of 4 orbitals, 1s and 3p. So the hybridization is going to be sp3 hybridization. There is going to be mixing of orbitals. We will get 4 hybrid orbitals, the sp3 hybrid orbitals. Now the 2 which consisted of only 1 electron, these are the ones which are going to form a sigma bond with the hydrogen atoms. The other 2 orbitals, they are the hybrid orbitals which are consisting the lone pair of electrons. So now what is going to be the geometry of the molecule? The geometry is in accordance with the sp3 hybridization, the tetrahedral geometry. But when we look at the shape of the molecule is a bent shape because of the repulsion of these electron lone pairs, and therefore the bond angle has decreased. In the case of the water molecule, the angle has now reduced further because of the presence of 2 lone pairs. Here it was 1 lone pair, here there are 2 lone pairs. So the angle has reduced further 104.5 degrees, right? So I hope now you can understand the geometry of the molecule is going to depend upon the type of hybridization. The shape of the molecule is going to depend upon how many lone pair of electrons it has. So the lone pair is distorting the geometry when we consider the shape of the molecule, right? The other examples you can see sp3 hybridization are CCl4, BCl3, NCl3. In all of them, what you have to do is just write down the electronic configuration. You will see how many bonds it has to form. So from that you come to know that whether it is forming those bonds in the ground state or it has to be excited. For first of all, write the electronic configuration in that way so that you get the desired number of half-filled orbitals. Once they are formed, you are just going to do a hybridization of those orbitals. You will get the desired hybridization. When you get the desired hybridization, you get the desired geometry, right? Once the geometry is formed, you have to just see how many lone pair of electrons they are present. How is that going to influence the shape of the molecule? So that would be all for this lecture. I hope the sp3 hybridization, this is clear to you. In the next lecture, we will be discussing the sp2 hybridization. We will be seeing examples where the molecules have the central atom undergoing a sp2 hybridization. So please do not miss any lecture. And now for that, what you have to do, just subscribe to the channel, click on the bell icon so that you get a notification the moment we put up the new lecture for you. And also do put your reviews in the comment section. This really helps other students to see how the lectures are, and they can also benefit by reading your comments. And also, if you have any doubts, feel free, mail us at h2ochemistry@gmail.com. You can put your doubts also in the comment section. We will be glad to help you all. And if you've liked the lecture, please do not leave before liking the lecture. And this really motivates us to prepare more lectures for you. See you again. Have a nice time. God bless you.